Mm. So hello everyone, my name is Shen, and today I am going to share our recent research with you. The name of it is State Shift and Gait Plan in a Feedback Linearization Control of a Tilt Vehicle. So these are the topics we will refer to. They are about feedback linearization, a control method. Let's move on to the first section. This is an introduction part. We will talk about the feedback linearization in UAV control. This is the dynamics of a quadrotor. Here, x is the state vector. It consists of the position and the attitude. U is the input. There are 4 inputs. So xs is a function of xs. Gxs is a function of xs. Specifically, they are fx and gx. But don't worry, this is the only equation we will talk about. So what you need to remember is that xs is the state vector, and the ui is the input. There are 4 inputs, u1, u2, u3, u4. So we can only control 4 states at most, but we have 6 degrees of freedom. So we can only control 4 of them directly. For example, we may control x, y, z, and psi as controlled variables. Also, we may control z, psi, theta, phi as controlled variables. Of course, there are other choices. In fact, this is the number of all the choices. Let's talk about the choice of z, phi, theta, psi. Calculate its second derivative. We receive this result. Here, h-axis on the right is the function of the state vector. Delta xs is a 4x4 matrix of the state vector. From this equation, we can calculate u1, u2, u3, u4. And this is the result of u1, u2, u3, u4. Now you may design a PD controller for z, phi, theta, psi, like this. It seems that every step is reasonable and solid, but let's ask a question. Since we need to inverse this delta matrix, it must be invertible. So my question is whether it is invertible. Actually, I checked the rank of it and found its rank is 4. So it is invertible. A simplified model can be used to test this controller before controlling the quadrotor. This simplified model can be a car. So this is the end of the introduction part. Let's move on to the next section. In this section, you will hear a novel system. The figure on the left is a tilt-rotor. The direction of the thrust can change. It is very popular recently. Unfortunately, there is no simplified model to design controllers. So we designed a simplified model for it. This is a 2-dimensional robot. There are 2 propellers to generate thrusts. Different from the conventional vehicles, this vehicle can tilt along this direction. So the direction of each thrust can change together. It may change the direction of the thrust like this. There are three inputs. They are the angular velocities of the left propeller, omega 1, the right propeller, omega 2, and the tilt angle, alpha. This is the dynamics of the system. You can see the inputs, omega 1, omega 2, and alpha. The output we are interested in is the position. The terms in the circle is a 2x2 matrix. I can write it in detail on the right. But don't worry, all you need to remember is that the term in the red circle is invertible. The inputs are omega 1, omega 2, alpha double dot. The outputs are x double dot and y double dot. Since the number of these inputs is greater than the number of outputs, this is an over-actuated system. One idea to control this system is using 3 inputs. However, there is a problem while using this idea. I call it state drifting problem. We will see this problem later. Another idea to control an over-actuated system is by discarding some of the inputs. Here, we only select omega 1 and omega 2 as inputs. Alpha is planned in advance. Thus, using this idea, we need to solve the Gait plan problem. As I mentioned, we need to plan alpha in advance. I will introduce these 2 methods in the next section. So this is the end of the dynamics of the model. We will discuss the 2 methods to control this tilt vehicle in this section. As I mentioned, there are 2 ideas in controlling this system. Let's focus on the first idea and its problem. There will be 3 inputs and 2 outputs. The first step is to calculate the third derivative of the outputs. We can get this result by calculating the derivative of the right side in the first equation. Differentiating this part generates omega 1 dot, and differentiating this part generates omega 2 dot. Differentiate this part, we will get alpha dot. So the result is this. Omega 1 dot, omega 2 dot, alpha dot are here as an input vector. The left x triple dot, y triple dot is the output vector. Delta here is a 2x3 matrix. Delta matrix has 4 row rank. We can calculate the input from this equation. The input equals to the pseudo inverse of the delta matrix times the output. And you may design your controllers here. In this experiment, I designed PD controllers. I will introduce this experiment. The initial position of the vehicle is marked in red. The reference is moving in a circle. And this is the result. Finally, the vehicle moves along a circle. So we may also check these results in a dynamic state arrow. The yellow line represents the dynamic arrow of X. The blue curve represents the dynamic state arrow of Y. Both of them become 0 finally. Now let's check the inputs. In the right figure, we can check 2 inputs, omega 1 and omega 2. The yellow line represents omega 1, the blue line represents omega 2. It seems that they overlap each other. But really, if I zoom this part, we will find that they separate when the time is large enough. Then, if I set the simulating time large enough, we can see that the inputs totally separate. No researchers reported this phenomenon before. I define this phenomenon state shift. Since the input separated, will the system still be stable? On the right, you can check the dynamic state error. It remains 0. This indicates that the system is still stable even if the state shift happens. But why is it stable? I will give an explanation in the next slide. This is our system. It is able to produce 2 thrusts. This is the reference. To follow this reference, the centripetal force is required. The green arrow represents the desired centripetal force. This centripetal force can be produced by F1 and F2 in this pattern. If we change the direction of the thrusts, F1 and F2 can also be like this. Moreover, F1 and F2 can be like this. In one word, to generate a specific centripetal force, F1 and F2 are not unique. That's why you see different F1 and F2 in a stable system. The state shift can happen in an over-actuated systems. So far, we have discussed the first idea and the state shifting problem. We know that the state shift happens in over-actuated system. How to avoid this problem? In idea 2, we discard an input. The direction of the thrust alpha is planned in advance. We have 2 inputs only. They are omega 1 and omega 2. The outputs are x and y. Since the number of inputs is equal to the number of outputs, it is not an over-actuated system. So there will be no state shifting problem in idea 2. But there is a new problem. How to plan the direction of the thrust alpha. This is what I call the Gait plan problem. As I said, the direction of the thrust is planned in advance. There are 2 inputs, and there are 2 outputs. This is not an over-actuated system, so there will be no state shift phenomenon. The new question here is how to plan the attitude. This problem is similar to the Gait plan problem in 4-legged robot. Let's move on to the circular reference. We plan the direction of the thrusts, always pointing to the center of the circle. This is the checking result. They are the dynamic state error. They become to 0. They are the inputs, omega 1 and omega 2. There is no state shift, but there is saturation. So these are all the topics in our manuscript. I will brief the further steps at last. On the right is the previous slide for the case for a circular reference. Although the result shows the stable in simulation, we have not found the stability proof. So finding the stability proof for a circular reference is one of our further steps. Notice that the stability proof for a linear reference has been found in our recent released manuscript. We found the proper Lyapunov candidate in that work. Another further step is about the application of this control method to a tilt-rotor. The cat-chote Gait was applied in our recent work to control a tilt-rotor. Thanks for your attention. Please ask any questions and provide your comments for the rest of the time.